Okay, so let's start. Today, I'm going to start a new chapter. Okay? We have defined equivariant cohomology, and we computed some examples. Now, I want to use differential forms to calculate equivariant cohomology. So far, the theory is topological, right? We assume that the group is a topological group in the definition. And then, to prove that there is a universal bundle, I assume that it's a Lie group. Okay? But basically, we were working in the in the continuous category. But now I want to work in the C infinity category. So I'm going to assume that manifolds are C infinity manifolds, and the groups are Lie groups, okay? And the action is smooth. Okay? Now, in the theory of manifolds, one of the most important theorems is Duran Theorem. Okay? Mm-hmm. So today is lecture 11. Now, Duran Theorem says that if you have a C infinity manifold, and omega is the complex of differential forms, C infinity differential forms on M, then the singular cohomology of M with real coefficients can be calculated from this complex, okay, of differential forms using the exterior derivative as the differential. Okay? So here, this is singular cohomology. And here, this is the cohomology of this complex that's called the Duran complex. Okay. Yeah, so it says you can use differential forms to calculate cohomology, singular cohomology. Now, in equivariant theory, there is also a Duran theorem. So the equivariant Duran theorem says that if a Lie group G acts smoothly on a C infinity manifold M, then the equivariant cohomology of M with real coefficients can be calculated from a complex that we have to construct, okay, of equivariant forms. And then there is a differential on this complex. It's not the exterior derivative, so I use a big D for it, okay? And this complex is called the Cartan complex. And this is singular equivariant cohomology. Okay? So what I want to do now is to explain what this Cartan complex is. Okay? And the elements of the Cartan complex are called equivariant differential forms. And then I will leave the proof of the theorem to the end, okay? Because, well, it's technical, and it might take a couple of lectures. Now, this theorem will allow us to use equivariant differential forms to calculate equivariant cohomology and to prove many theorems about equivariant cohomology. Okay? And, well, so I have to assume that you know about differential forms, you know about the exterior derivative, and you can learn that in my book on manifolds. Now, there are a couple of operations on differential forms that you have to know, which sort of comes at the end towards the end of the book on manifolds. So I don't know if you all know it. They are interior multiplication and the Lie derivative. Okay, and usually when I teach the course on manifolds, it's one semester. I usually don't have time to cover that section, because there are other things I consider more important, like the integration. So I usually skip over that. And for that reason, so today, in the first hour, I will go over interior multiplication and the Lie derivative, okay? And I will omit most of the proofs, but you can read the proofs in that book. Okay? Yeah. So today we're going to look at interior multiplication and the Lie derivative. All right? Now, I'm actually going to start with the Lie derivative. Now, you can define the Lie derivative of a vector field or of a differential form. So let's start with the Lie derivative of a vector field. Okay, so the Lie derivative is a kind of derivative, okay? So that means you're trying to differentiate, okay? And you have two vector fields. So you have two vector fields. Okay, this is the notation for C infinity vector fields on M. Now, so let's say this is the vector field X. Now, a vector field is a vector at each point of the manifold. And if you have a vector field, then through each point, you have a short piece of a curve called the integral curve. So through P, you have a curve called the integral curve. So the integral curve is a curve whose derivative is the vector field. Okay? So we have a point P in M. And then X has an integral curve through P. Okay. Now that integral curve I will write as phi t of P. It depends on T. So phi, it's a function from a small interval across an open, oh, I see. Yeah, so, okay, so this, P is fixed, okay? But this function, let me see, I'm getting, well, no, let's not do this. That's it. Yeah. So, yeah. So P is fixed, so this is just a function of T. Okay? And so phi of T as a function of T, it's defined on some small interval about the origin, such that at time 0, it's P. And then if you differentiate with respect to T, you get the velocity vector, and so you get so the velocity vector at time t is the vector field at phi t of p. Okay. Yeah. So that's the integral curve through p. Right? So yeah, it's a curve that looks like this. Now, I want to calculate the derivative of y with respect to x. So to calculate the derivative, right, you need to take the difference at two different times, subtract them, divide by t, take the limit as t goes to 0. Okay, so at time 0, I'm here. At time t, I'm here. Let me draw a different picture. So at time 0, I'm at p. At time t, I'm at phi t of p. Okay? And y has a value there, so this is the vector y at p, and then here is the vector y at phi t of p. Now to calculate the derivative, I want to calculate the derivative of y. So I want to take y at time t. Now I would like to subtract y at time 0, right? And then divide by t, and then take the limit as t goes to 0, right? That's what I like to do if I want to calculate the derivative. Now, why can't I do this? Like,
you cannot compare different tangent space.
Yeah, because these are two vectors at two different points, so they are in two different tangent spaces. They're in two different vector spaces, so you can't subtract them. Okay? In order to subtract them, they have to be in the same vector space. Okay? Now, okay. Okay, now I define the integral curve here. However, actually, the theorem is a little bit more general in that you could vary this p. Okay? So, actually, the theorem tells you more than this, that in fact, this phi, so there exists, for any vector field, there exists an epsilon greater than 0, and a neighborhood U of P in M, okay, such that this, you can actually vary the p. So this phi is defined on minus epsilon epsilon cross u into n. Okay? And so phi, now let's see, phi at time 0 for any q is q. For all q in u. And then, and then you actually have the integral curve. You have not just that one, but you have all these integral curves, okay, in the neighborhood of p. Okay? So dt of phi t of q is x at phi t of q. Okay? So you actually have this. You have more than one integral curve. You have all of the integral curves in a small neighborhood. Okay? So you see, now so phi t, for a fixed t, it actually maps from u to the image, so phi t of u in M. And it has an inverse because phi t, in general, phi t composed with phi s is phi t plus s, wherever they are defined. And so this has an inverse, phi minus t. So phi t from u to phi t u has inverse phi minus t from phi t u back to u. Okay? In other words, phi t is a diffeomorphism. And so let's go back here. You see, I have to bring this tangent vector back to P. Okay? So what is a map that will take this point to P? What's a diffeomorphism that will take phi of t, P, back to P? Phi of minus t. Okay? So phi of minus t will take this point back there. It will take this tangent, its differential will take this tangent vector back here. Okay, so that is phi of minus t, the differential. And now I can subtract. Okay? And this is the definition of the Lie derivative of y with respect to x at the point P. Okay? So this is the definition. This is the definition of the Lie derivative. Yeah. That's the Lie derivative of a vector field. Okay? Now you can also write this as, you see, this is really just this function evaluated at 0. Because at 0, you have the identity. Okay? So this is also the derivative of this function of t, phi of minus t lower star y phi of t at p. Okay? This is a function of t with values in the tangent space at p. And if you differentiate that function at 0, that's this, right? Okay, so you can also write it like this. Okay. Okay, so that's the Lie derivative of a vector field. And now let's see. Let's define the Lie derivative of a differential form. Okay, so let omega, say, be a K form on M, okay? A C infinity K form on M. And I want to define the Lie derivative of omega. And X is still a vector field. And this is the integral curve of the vector field. So here is omega p, omega at p, and then omega at phi t of p, okay? So again, they are in different vector spaces. So in order to compare them, I have to bring this back here. And now, which map do I use? The pullback, right? The pullback by, well, the map phi of t takes this to this. So if you pull back by phi of t, this will go back there. Okay? Therefore, you should take omega phi t of p, and then you take the pullback by phi t. Okay? Then it will be here. And so you can subtract omega p, divide by t, take the limit as t equal to 0. Now it's phi t, right? Because phi t is the map that takes p to this, and you just pull it back. So there's no minus when you are calculating the Lie derivative of omega at p. Okay? So that's the definition. Yeah. Okay, now, yeah, so what does the pullback mean? Recall, the pullback is a K form here. So you apply this to K tangent vectors at P. Okay? So if V1 to Vk are tangent vectors at P, then this pullback, by definition, it's omega at phi t of p, okay, of, now you have to push these vectors forward. So phi t lower star v1, phi t lower star vk. Okay? That's how the pullback was defined. Okay, now, a zero form is a function. So what is the pullback of a function? Function f on M is a zero form. That means it has no arguments. At each point, you just have a number. Yeah. So the pullback of a function has no argument, right? So it's got this empty argument. And if you apply the definition, then it is the function f at so just a minute. So we have the okay. Now let me see. I think it's not worth doing. I was trying to derive the definition of the pullback of a function from that, but I think we should just assume that k is greater than or equal to 1, and just make a separate definition for the pullback of a function. It's easier. So the definition of the pullback of a function is composition. So if, say, h, is a map from n to m, then the pullback is just the composition. Okay. Yeah. So you have n mapping to m by h, and then f is a function. So the pullback is just a composition, f composed with h. Okay? And so what's the lead? Now the lead derivative of a function. Let's see. Yeah. So we need to define the lead derivative of a function. So LXF. For a function, you can, right? Yeah. So for a function, the values are in R, so you don't need to do that. Yeah. So it's just f at phi t of p minus f at p over t. Take the limit as t goes to 0. And in fact, this is the pullback of f evaluated at p. So it's somewhat consistent, right, with that definition. Now, this is the same as XF, because that's how you calculate XPF. To calculate XPF, you take the integral curve, you evaluate f on the integral curve, and then compare and take the difference, divide by t, take the limit. So, yeah, that's the first property of the lead derivative. So the lead derivative of a function doesn't give you anything new. It's just XPF. Okay? And there is a theorem that says that the lead derivative of a vector field, okay? Now, at each point, you get a vector. So this is a vector field. And this vector field turns out to be the same as the bracket. So for a vector field, the lead derivative also doesn't give you anything new. Okay? And this is a somewhat messy computation. Yeah, but it is done in my book. if you don't have time, you can just assume this because, going through the calculation actually doesn't shed any insight. Okay, and okay, now let me define interior multiplication. Now, the Lie derivative, it cannot be defined just as a single on a vector space because you need the values of the vector field nearby, right? So you cannot define the Lie derivative of a vector. It has to be the Lie derivative of a vector field with respect to another vector field, okay? Because you need the values nearby. But for interior multiplication, you can define it at a single point, without any other points nearby. So you can define interior multiplication on a vector space. Okay, so let V be a vector space. And for me, a vector space is always a real vector space, okay? Now, a K covector is an alternating K linear function. So a K covector on V is an alternating K linear function on V. So that means it has K arguments, okay, and goes into R, and it's alternating. When you switch two arguments, it changes sign. So, and I have a notation for K covectors. I write either it's alternating K linear functions on V, or I write this as lambda K of V dual. It's the Kth exterior power of the dual vector space. Okay? And now, if V is in V, then I define the interior multiplication of V applied to alpha to be a K-1 covector. So this is lambda K-1 V dual. Okay? And that means it takes K-1 arguments. Okay, so if you have K-1 argument, then you just put V in the first argument. Okay, so that's the definition of interior multiplication. Okay? Now, obviously, if you apply interior multiplication twice, then you are going to have V twice. So IB alpha, if you apply V twice, then you lower the degree by 2. K minus 2. And well, then this is IV alpha V, V1, Vk minus 2. And then this is alpha V. You put V in as the first argument again. But because alpha is alternating, this is 0. Okay? So that's the first property of interior multiplication, that if you apply it twice, you get 0. Now I'm going to list all the properties of interior multiplication and the Lie derivative that you need to know. Properties of Lie derivative and interior multiplication. Oh, sorry. Yeah, I defined it on a vector space. Now I want to define it on a manifold. So interior multiplication on a manifold. On a manifold, you just define it point-wise. But, yeah, so actually, and you can define it globally also. So if X is a vector field, and then omega is a K form, and Y1 to Yk minus 1 are vector fields, then, okay, Ix omega, that lowers the degree by 1, so you apply it to K minus 1 vector fields, and that's omega, again, put X in as the first argument, Y1 to Yk minus 1, okay? So you can take this to be the definition of interior multiplication on a manifold. And now let's just make a list of all the properties of interior multiplication. Lx and iota x. So theorem 1. Now, so the Lie derivative on differential forms, it takes a form to a form of the same degree, but it is a derivation of degree 0. It has degree 0 because it does not increase the degree. Okay? It does not increase or lower the degree, so its degree is 0. And to say that it's a derivation means that if you have the wedge product of two differential forms, then it satisfies the product rule. Okay. It's a derivation. And then it commutes with D. So Lx followed by D is D followed by Lx. Okay. And the third property is a product formula. Well, I call it a product formula because it looks like a product formula, but it's not really. These are not really products. So if you take the Lie derivative of omega of y1 to yk, okay, so where omega is a k form, and the rest are vector fields, then omega applied to y1 to yk is a function. Okay, so the Lie derivative of that function, it turns out that it looks almost like a product. You just take the Lie derivative of each of these things. So you first take the Lie derivative of omega, and it's still a k form, so you apply it to y1 to yk, okay? And then you take omega, and you take the Lie derivative of each of these arguments, okay? So I goes from 1 to k, is y1. You're supposed to take the Lie derivative of each one of them, yi, one at a time. So you have k terms because you take the Lie derivative of the k arguments one at a time. And that's the formula. So I put quotation marks around the product because, well, omega applied to this, that's not really a product. But it almost looks like the product formula. You differentiate each factor one at a time, okay? So that's what I call the product formula. Okay, so these are the properties of the Lie derivative. And then let's now write down the properties of interior multiplication. So iota x, it goes from all the forms to all the forms, but it lowers the degree by 1. So that means it has degree minus 1. And it's not a derivation, but it's an anti-derivation. Degree minus 1. Okay? So that means it's almost like a derivation, except there is a sign. So iota x omega wedge tau plus. And the rule is that whenever you move something across something else, then there is a sign that the product of the two degrees. Okay? Yeah. So this is degree minus 1, so it really should be the degree of, no, so it should be minus 1 to the minus 1 times the degree of omega, because I'm going to move x across omega. Okay, you see, these two I'm commuting. So it really should be minus 1 times the degree of omega, but that's the same as just the degree of omega. Okay? Yeah, okay, so that's an anti-derivation. And then you already know that Ix composed with Ix is 0. Okay? And then there's a very important formula. It's called Cartan's homotopy formula. Oh, just a minute. I started, right. I started at 3:30, so yeah, I still have a couple of minutes, right? So Cartan's homotopy formula. It says that Lx is dIx plus IXD. Okay. All of these formulas, this formula is actually fairly easy to prove because D and I are antiderivations. Now, if you have two antiderivations and you form this sum, then it's a derivation. So both sides are derivations. And therefore, if you can show that they agree on one forms, then this will give you everything, because locally a K form is just a product of one forms. Okay? So actually, to check this formula, you only have to check it on one forms. And you actually have to check it only, and one form locally is FDG. So you only have to check it on a function and on DG, and that's fairly easy. Okay? And then the fourth property is that IX, it goes from forms to forms, is F linear. Okay? That means Ix of a function is F linear, so this function just comes out, Fix of omega, okay? For F C infinity function on M. And that I sometimes write as capital F. Okay? So interior multiplication is F linear, but the Lie derivative is not F linear because it's an antiderivation. So, the Lie derivative of a product it is going to be LXF omega plus F LX omega. So it's not linear. You have an extra term. Mm-hmm. So LX is not F linear. Okay? Okay. Let's take a break for 10 minutes. Okay? And then in the next hour, then I'm going to go back to equivariant cohomology and principal bundles. Okay?